So good morning, everyone. My name is Alexis Tyndall. I'm the Manager of Digital Innovation here at the University of Adelaide Library, and thank you all for joining us for today's Digital Humanities Lab webinar. This is the second in this year's five-part series. So before we start, I'd just like to mention I live and work on the lands of the Kaurna people, and I'd very much like to acknowledge and pay my respects to them as the traditional custodian on whose ancestral lands I am, from whose ancestral lands I'm joining you. I acknowledge the deep feelings of attachment and relationship with the Kaurna people and country and respect their past, present and ongoing connection to the land and cultural beliefs. As this webinar is online, it's very possible that you're joining us from other parts of Australia, so I extend that respect to relevant communities in other regions, and I especially welcome any Aboriginal and Torres Strait Islander people who are joining us today. With this webinar series, the University Library hopes to inspire and inform humanities researchers and their potential collaborators who are interested in using digital approaches in their work. When I say potential collaborators, I mean everything from researchers in other disciplines, representatives of the galleries, libraries, archives and museum sector, students and whoever else is interested. Everyone is welcome at these webinars. We showcase real projects and researchers that are using data, digital tools or digital research methods to drive, to enrich, to complement or communicate their research. Just a couple of bits of housekeeping before we get started. Today's session will be recorded and shared after the event on the University of Adelaide YouTube page. As a registrant, you will be sent a link to that recording. We will have all of our presenters first today and then bring them back for questions and discussions at the end. If you have any questions, please look to the bottom of your screen and you can see the chat icon and you can ask your questions in that chat window. Feel free to introduce yourself in the chat as well and let us know where you're coming in from today. Your questions can be sent through at any time and I will collect them and pose them to our speakers at the end. Online, we've also got my colleague Matt Lumsden, who is helping us today, and we're keeping an eye on that chat window for any technical questions you might have. So we have a lot to get through, so without any further ado, we will be hearing about 3 projects today, all of which are centred around musical instruments. They include everything from researchers working with traditional instruments found in historical collections through to those that are creating brand new instruments, enabling new forms of music and engagement and performance. So first up, we have Dr. Anthea Skinner from the University of Melbourne and Victorian College of the Arts and Dr. Alan Ilsar. Anthea is an ethnomusicologist who specialises in disability music culture, military music, organology and archiving. Anthea's research into disability music focuses on professional musicians with a disability, their creative output and career pathways, as well as adaptive musical instrument design. She is a musician herself with the all-disabled Bear Brass Asylum Orchestra. And Dr. Alan Ilsar is a drummer, composer, instrument designer and researcher who is researching the uses of a new gestural instrument he co-designed, the AirSticks, at Monash University's Sensi Lab, the field of health and wellbeing, making music creation more accessible to the broader community. He too is a musician, having played with a range of theatre productions, orchestras around the world and contemporary artists. And with that, I will vanish and hand over to Alan to get us started.
Thank you, Alexis. I'll just share my screen. So yeah, I feel really lucky to be part of this project. The AirSticks and the Air Dancer, adapting a gestural controller for a dancer with disability. I'll try to give a quick background to the AirSticks as an instrument, and then we'll speak a little bit about Melinda Smith's practice and how we adapted that instrument for her practice. And yeah, it's a very much an ongoing project, so we look forward to presenting more work in the future on this. So firstly, what are the AirSticks? Basically, my background is as a drummer, and I wanted to combine the expressiveness of acoustic instruments with the endless sonic possibilities of electronic music. And that's me holding the AirStick. Here's the AirStick here. This is the latest one. We'll get to this. I'll give you a quick background on what the system overview. So basically, the AirSticks at the moment have a 9 degrees of freedom IMU, a Nordic BNL microcontroller that sends information via Bluetooth to a computer. On the computer, we have a bit of software that we call Airware, and that translates the gestural data into MIDI or OSC, and that gets sent to a music software. I often use Ableton Live, but we can also use Max or Logic or Cubase or whatever we like to use. We've also triggered synthesizers with it. and so forth. So it's very open. And because we're talking more specifically about hardware here, I thought I'd give an overview of all the different hardware. And when I started looking at what I've been doing the last 15, 16 years with this, I realized there has been a lot of prototypes. The first one on the top left is using camera. We had basically a camera detecting a mallet and using the shape of a square to see how close it was to the screen or further back. But this was 2007 and the cameras were quite slow then. So we tried an exoskeleton there in the middle, and that was very clunky. And then we sat for a very long time on the Razer Hydra gaming controllers, which were an off-the-shelf product, a VR controller. But I always dreamed of building my own hardware for this project, which is there at the bottom left, is a CAD of what we wanted to create. And during my time before joining Sensilab, this was some of the development we had made in the bottom here. So my PhD centered around my own practice as a drummer and electronic producer using the Razer Hydra gaming controllers to create gestural music. And then when I started at Sensilab at the end of 2019, we started to develop our own Airsticks, what we call 2.0, which uses our own custom hardware. Here's one that you can see. This is the first prototype we made of Airsticks 2.0. As you can see, it slots onto a drumstick very easily because I'm a drummer, and it was within my own practice that I wanted to use this. But it's also got no buttons. So the point of this was to become a much more accessible instrument in terms of being able to just grab it, move it, not worry about pressing buttons, map it in a really, in a way that was quite intuitive for people to use for the first time, and then develop it further with them in terms of what sounds they wanted to make and what movements they wanted to make those sounds. So we developed that further for drummers as well, just to take another point. This is the Airsticks 2.1, which also has a sensor at the bottom that you can squeeze sound out of. So just to talk about the printing part of this a little bit as well, these are all printed from sintered nylon, which, as you can see there, is the process. It's kind of magical. This is not my field, but they pop out as this hardened material, and then we shave them off, and these are the parts that we put together, this Airstick at least. So yeah, I'd like to try to move on and quickly play a video of the first day, the first session, where I had 2 of these sticks, and I worked with Melinda Smith, and then Anthea can talk a little bit more about Melinda's practice.
Shall we leave it there, given we're very tight for time?
Yeah.
Oh, can we go back just so we can see Melinda while I talk about it? There we go.
Yeah.
Thank you. I'm Dr. Anthea Skinner, and my field of expertise is disability music. So when I came into this project, my aim was to look for professional artists who hadn't had access to instruments before. And I, for about 15 years, have worked on and off with Dr. Melinda Smith, who is a professional dancer with cerebral palsy. She's also hard of hearing. And immediately, the work Alon was doing with the Airsticks seemed like a really obvious thing to work with Melinda, because, you know, as you can see, this was literally her first day using it. You know, you don't need to be able to read music to use it. You don't need to be able to have an in-depth understanding of sort of music theory. And so we thought this would be a really great starting point for Melinda. And as you saw, this is her first day. What we then did with Alon, obviously Alon already had a really functional musical instrument, but we then worked to make it suit Melinda more specifically, both in relation to her disability and in relation to her actual performance practice, which in some ways, for me, turned out to be the more exciting part, I think, and I think Alon would agree. So on the first day, for me, looking at Melinda here, she's clearly playing it really well. But when you have cerebral palsy or sort of any kind of muscular sort of spasming issue, the grip involved with holding the drumstick like that actually takes a massive amount of concentration. So when I'm watching this, someone who doesn't know Melinda's work will see it and say, wow, she's making beautiful music. What I see is she's very limited in the way she can move because she's concentrating really, really hard on holding that instrument. So we then started looking at different ways that she could hold it. I think we first started looking at maybe creating a glove that would actually hold the stick, because we really love that sort of flick that you can get with the stick. But as we moved forward, we started to realize that perhaps something that would hold to her body would work a lot better. And we started working with a costume designer to help that happen. Musically speaking, though, I think that's where she really surprised us, in that I had seen this as a musical instrument. I know Alon had done a little bit of work with poetry before, but Melinda is a poet, a published poet as well. And the first thing she wanted to do was to put her poetry into the machine so that she could point in various directions and play lines of poetry. So she ended up with this wonderful music poetry collaboration in and of itself. We recorded her Melinda doesn't speak very clearly as a result of her cerebral palsy, so we recorded the poem in her electronic communication voice, like an electronic voice. And we also had her speak it in her own voice, which people often struggle to understand. But by layering those two things, it sort of gave a deeper level of understanding. I was just joking sort of earlier that our main tactic when it came to redesigning the shape of the air sticks to suit Mel is I call it the take it and break it technique. We sent the instrument home with Melinda, and I think within 6 hours she'd broken it, broken the charger, because she has limited hand movement, and that's really what we wanted to know, where are the glitches for someone with the kind of hand movement of Melinda, what's not working for her, what is. So by repeatedly breaking the instrument, we then gave Alon information that allowed him to come back and redesign and redesign and redesign until she couldn't break it anymore. And now it's still gives the music that she wants, but she can't break it. And that is wonderful. And that's really important, because there's no point in having a piece of technology if you need to constantly have it fixed, or have someone else turn it on and off for you. Should we move on to the next bit, Alon?
Sure. Yes.
Very aware of time.
So we came up with an idea of basically at first strapping this air stick that we had onto Melinda's wrist with a wristband, and then she did her first performance of a piece called The Rhythm of My Body Shapes with this technique. But as an instrument for her to take home, this wasn't accessible. It had no way for her to press any buttons on it to change to other settings when she was rehearsing, and it also had a very small on-off switch and a recharge port that was quite difficult to make new chargers for. It's not a standard USB. So we went on to create a touch-sensitive and pressure-sensitive pad on top of something like this, in the form of this new air stick, which is a bit bulkier, but because she's wearing it, that's not a problem for us or for her. So this is where I've taken off the pad, but this is where the pad will sit for her to be able to slide her finger on this or touch it. But also the button is a lot more accessible. And I went and visited her and brought her some new buttons to make sure that she could switch this on and off, but not switch it on and off accidentally as well. So that's the kind of compromise that we came to. So that's it there, with a strap through this little, if you can see, we've created a gap in the print. And again, this printing is so strong. This form of printing is so strong that we can afford to have this very thin bit of plastic that's not going to break when you put a strap through it. So that's, and there's also a light, and so she knows it's charging, and it's using normal USB chargers now as well. So these are all the things that we looked for to make this instrument more accessible within the hardware. Within the software is a whole other thing, and maybe not so much to be discussed as part of this conversation.
So finally, now that we have a prototype that fits onto Mel's body, our next step is creating what we call the Air Dancer harness. And we've been working with Anna Cordingley, who's a costume designer at the Victorian College of the Arts, to do that. So here you can see their basic designs, and I don't know if you can see the sort of little pink outlines on her arms, that they're the little pockets where the air sticks will go. There's little pockets as well on her legs, and there'll be one on her chest. And I really wanted to show this picture mainly, I guess, to give you an idea of sort of what working with Mel is like, because I envisage this as a sort of very utilitarian, sort of black and white, harness. Mel, as well as being a musician and a poet, a dancer and a poet, is a painter. And she said, well, can't we make it look pretty too? So she and Anna got together, and they're actually going to be laser printing Mel's designs onto the Air Dancer harness. And indeed, that's something that we can change for different performances and for different artists if we ever, decide to make it sort of more available. So that's us. That is the Air Dancer and the Air Sticks. And I'll hand over to Aaron and Kim.
Thanks so much, Alon and Anthea. That was really, really interesting presentation, and thanks so much for sharing that video as well. It's wonderful to see. So coming up next, we have, let me just say, Professor Aaron Corn and Dr. Yonak Kim. Aaron is presently the Director of University of Melbourne's Indigenous Knowledge Institute, and was previously the Director of the National Centre for Aboriginal Language and Music Studies and the Centre for Aboriginal Studies in Music here at the University of Adelaide. He has decades of experience of close collaboration with Indigenous colleagues, working towards broader recognition for the significance of Indigenous knowledge through multiple research and education initiatives. Kim is a mechanical engineer whose research interests explore mechanical and chemical properties and study the structure of various biomaterials to combine engineering tools. Working with multidisciplinary teams, he has been developing 3D visualization technology for imaging and reconstruction of biomaterials. And I invite them to join us. I can see you, so take it away.
Thanks, Alexis. And thanks to the University of Adelaide for having us today. And to all other speakers on this panel. I'm speaking from the land of the Woiwurrung and Wurundjeri here in Melbourne. And as Alexis said, I'm currently inaugural director of the Indigenous Knowledge Institute at the University of Melbourne. And until recently was director of the Centre for Aboriginal Studies and Music, CASM, at the University of Adelaide. So the project that brings us all together is a linkage project funded by the Australian Research Council, the ARC for short, that I'm the lead chief investigator on, and Anthea here is one of the other 8 chief investigators, and everybody here is connected to those chief investigators one way or the other through the work that they do in their various institutes and labs. And that project is called 3D Printing of Custom Musical Instruments for Heritage and Industry Needs, which is a boring but efficient way of talking about all the bases we're trying to cover in that project. I think it's quite a unique project because for the most part, 3D printing technologies haven't really been applied to producing sound producing instruments in a way that enables them to produce sound as intended by their original models. But before I get into that, the partners on the project at an institutional level, and there are honestly just too many individual people to name on this project at once. There are a lot of people on it. So when this goes live, Alexis will make sure that we've credited everybody sufficiently. But the institutional partners are the University of Adelaide as lead organisation, Monash University, the University of Melbourne, the Mulka project in Yirrkala in the Northern Territory, which is a local Indigenous-led community archive in the town of Yirrkala in northeast Arnhem Land, which is a leading example of what locally, Indigenous-led Indigenous archiving can look like. And the South Australian Museum is the final partner organisation there. And we conceived of this project as a highly interdisciplinary approach and team. And we have a whole range of people who work on the project, who span disciplines like, but not limited to, ones in music, computer science, museums and collections, material culture, conservation. So, you know, the physical maintenance and restoration of things, engineering, including acoustics, and until recently, because there was a you know, sad and untimely passing away of one of the members on the team, one of the Indigenous community leaders at Yirrkala, from Yirrkala. And there is also a growing constellation of other intersecting projects with this one that has brought us all together, like the one that Anthea and Alon, that's funded by various means, are working on through the ASTICS that they've just exemplified. So it's good in a way that, despite the challenges of being locked down and not being able to get into labs, and, you know, having to wait long times for, you know, the right computer chips to become available to manufacture the equipment that we needed, that then got held up in shipping delays over the past 2 years. It's nonetheless great that this project has already, in a way, outgrown the original vision and picked up momentum and gone in a whole bunch of intended and unintended directions. That's one of the great strengths of what we do. So when we first came to the project, and it went through the ringer with the funding body several times before it was finally funded. So it had various iterations of development and tightening up before we finally got over the line to land the funding. We wanted to test how 3D printing techniques could work for both preservation and documentation outcomes, initially effectively from a museums and collections context, because that really hadn't been done before. The other challenge, of course, is that even though 3D modeling has been used for non-sound producing, non-musical artifacts as a way of preserving them, the added challenge of trying to document what a musical instrument is and how it works is, does it actually work? If you scanned something and then print it, will it still make a sound that's anything like the original? And so there are limitations with the kinds of printing materials you can use, but there are also opportunities, because what we soon discovered as the project was being refined over the 3 or 4 years we were talking about it, is that, well, what if we could make playable scans and prints of instruments of various kinds? And what if, in some cases, the materials that we could use, and I'm thinking, very high-tech materials at the moment, like, carbon fiber and fiberglass, what if those kinds of materials could actually produce instruments that were more robust than the originals in some cases? Because, a lot of musicians around the world, particularly ones who play instruments made of wood, won't travel on planes on long flights to other parts of the world with their best instruments, because instruments made of wood have a terrible tendency to crack in the holds of planes due to temperature and humidity fluctuations. And there was one thing that really stuck with me as I was writing the application about how this could be possible, because there's a very, very famous Australian band that I worked with for many years that toured the whole world with a didgeridoo, or yiraki, to use the Yolngu term from Northeast Arnhem Land, made of fiberglass. It was actually cast from an instrument that had been made from wood, then split vertically down the middle and cast on both sides, made out of fiberglass using traditional surfboard making techniques, and glued back together. It was painted, and nobody ever knew that that instrument was fiberglass, which is why I'm being a bit cagey about which band that was precisely. Nobody ever knew it was fiberglass. They never told anybody. They never advertised it. It weighed as light as a feather. You could pick it up and, you know, just be surprised at how light it was given its size. And it never cracked. It never warped. It never failed. A wooden instrument would eventually just have, you know, completely been destroyed by temperature and humidity fluctuations in the hold of a plane. So that really got me thinking about how this project could be more than merely about preserving instruments that exist, but what about adapting them in a whole bunch of ways that hadn't been considered before, to be, you know, more robust or more affordable? What about adapting instruments for the kinds of people who Anthea and Alon are working with at the moment, who at the moment don't really have access to cheap and affordable bespoke instruments that, if you're using traditional manufacturing methods, cost a fortune to make for an individual. It's completely unaffordable for most people, particularly people living on a disability pension. So what can we do in that space became the real sort of question of the application and the work that we're doing now. So before I finish, I just want to talk about some of the novel challenges that we had to consider, because ultimately there's not much point producing musical instruments that can't be used as musical instruments, okay? If we're talking about anything than beyond a cosmetic, dead display it behind glass in a cabinet approach to making a replica of something. If you actually want to use these technologies to make functional musical instruments, there's a whole range of things you've got to think about. So to replicate instruments properly, and particularly ones held in collections, you actually just can't destroy them. You can't slice them down the middle and scan their insides. Their insides, of course, their resonators, are absolutely integral to sound production. So unless you're scanning the internal structures of an instrument, you're unlikely to make anything that will sound remotely like the original. You can't just scan something with a handheld device externally and expect to produce an instrument that is in any way faithful to the original. So we've had to come up with a range of non-invasive methods for scanning the interior structures of the instruments that we're seeking to print. And there are a range of techniques for how to do that. You know, some of it, you know, involves, you know, sticking instruments into, you know, MRI machines, you know, X-ray, you know, ultrasound. They're all non-invasive techniques. You know, you can feed speckle lasers, you know, up pipes, so, you know, like into the bores of wind instruments. And, you know, there's, you know, even a robot arm that's been worked on at Monash to, you know, send tiny scanners up. All of that is still really being prototyped at the moment. And we have another interesting and novel challenge as well, because, you know, a lot of musical instruments are bigger than most commercially available 3D printer beds. So how we deal with that is another great question. Every time a printer comes onto the market that can scan, you know, that can print, you know, bigger instruments, we look at it very closely. We just Anthea just found an infinite printer that runs on a treadmill that we're currently looking at trialing. And then, you know, we've got other options other than finding bigger printer beds or infinite printers. You know, we just sort of make the instrument in parts and glue them together. That's another option, and that might work for instruments that are made in parts and nailed together traditionally. It probably would be less satisfying for something like a didgeridoo, which is, you know, a long pipe, however. So look, you know, they're the various engineering challenges that we have, and I think I've gone pretty much over time, so I'm going to throw to Kim. So thanks.
Okay, thank you, Aaron. So let me share my screen so we can talk about what I did or what we did for 3D scanning and printing of in an Idaki. So I'll start. I'll start talking about some like 3D scanning techniques. Aaron covered a little bit as well, and what challenges we have with these 3D scanning techniques when we're scanning to Idaki. And we're going to talk about the prototype 3D scanner we developed and some challenges and results with regard to 3D printings. So most common 3D scanners you can see around the labs around the world or around your homes are like the handheld 3D scanners. They're relatively fast, really easy to use. They're quite accurate, and the interesting thing is that because they use cameras, they can actually capture the textures and the colors and images around the object you're trying to scan. But one of the issues is that it requires a lineups of sight. So if you can't see, or if the scanner can't see it, you cannot scan anything. So like an Idaki or any other wind instrument that has an internal like tubes and internal structures, this is not really suitable. So what about like CT scanner, MRI scanners like this? Like this micro CT scanner, this example, what I did before with the Clay Ocarina, it gives you phenomenal, amazing results. It can even scan tiny little grooves and engravings on the instruments. You can see inside, of course. And but the downside is that first thing, it takes extremely long time to scan. I believe it took the Ocarina is around like 15 centimeters wide, and it took about like 36 hours in total to get the model. So first thing, it takes very long, extremely long, and there is a size limitation. So like an Idaki that goes at least 1 meter to several meters long, you can't really use this type of 3D scanners. Then what about like just measuring the instruments, drawing out using computer-aided design to model it? This is very viable for most cases, but like this like Achilles oboe, you can measure the diameters on each sections and diameter of the fingering holes, and assuming the internal tube is straight, you can relatively easily model this kind of instruments. However, like an Idaki that has a amazing organic shapes, there's curvatures and grooves inside. So those are something that is challenging using this kind of 3D scanning or 3D modeling techniques. So like challenges in the scanning is that, as you can see in the images in the slides, there are very organic shapes, something you can't really measure and model easily. And because of this wind instrument, there's an internal tube you can't see inside. That means we can't use handheld scanner. With a large size, even if we can't use any micro CT scanner because of organic shapes. We can't use any SolidWorks or any 3D modeling software. So we had to come up with something new that can scan the instrument inside of the instrument along the length. And we developed a prototype 3D scanner that uses a laser line module with a 45 degrees mirror that reflects the laser line and endoscope camera that looks like this. So what it does that it shoots out the laser and bounces the laser line off the mirror, 45 degrees mirror, and illuminates the sort of the single layer, I would say a single layer of the instrument, and with a laser line. And it creates a contour following that, following the instruments. And by repeating, so we do these scans along the length. In this particular example, we did every 10 millimeters increments along the length. And after each scan, we rotate the instrument roughly like 90 degrees because the laser line can't really create the entire contours of the instruments. rotate the instrument 90 degrees and repeat the process like 4 times. So with the laser images we captured, we align those laser images and using the 3D software, we can create a point cloud, which is one of the formats of the 3D models. And from this point cloud, we can create a 3D mesh structures, which is file type for 3D printing. So for internal images, we follow those steps. For external scanning, we use something relatively more simpler. We're using photogrammetry techniques, where you take images of the object you're trying to scan, in this case, Idaki, in around the model and multiple images, and using trigonometry techniques, using like following the multiple points on the instruments, and in like placing the camera in virtual 3D environment, and using those and by merging those images captured, you can create 3D structure of the Idaki's external features. And since we had like now internal and external 3D models, now we can merge them together to create a single and final 3D models and Idakis. As you can see, we have quite accurate external features, and we also have an internal tube structures model that as well. So with this model, we can put it into any 3D printer and print it out, and it comes out like this. And to give you a perspective, and there's a pen next to it to give you a sort of scale, what you're seeing. So as you can see, the printed result is very, very small. It's only a few centimeters long, and you definitely can't play this. The issue with this is that there are some limitations with 3D printings. Obvious limitation is first the size. Most of the conventional 3D printers, FDM 3D printers, or you have in your homes, can print maybe up to 250 millimeters, maybe 300, reaching at the maximum limit. Whereas Idaki itself is like 1.5 meters long, so you can't really use that. As Aaron talked about before, there are like new 3D printers that use a treadmill system that you can technically print infinite lengths, but the setting up can be a little bit more challenging. And imagine the print failure in the middle of the fail. That means like you wasted so much time and materials as well. Other way, you can print a small section by small section and glue them together. If you can imagine like blue saxophones and clarinet, you put multiple sections together, you can do something like that. But like to print out the entire instrument in a like single print, it is still some sort of challenge. And another challenge is the material. Most of the 3D printers uses either resin or wood, plastics, whereas Idaki is in wooden instruments. So there are certain qualities that the wood produces in terms of sound quality and the resonance. So there are some 3D printing filaments that infuse with wood grains and wood dust, but because it is small amount of wood dust infused with plastic, it's not really, it have like same quality as wood. There are other materials like fiberglass or carbon fiber infused with plastic filaments, but still those things as well. The reason fiberglass and resin produces like good, really sound quality and good resonance because it's fibrous structures. However, those infused plastic filaments uses a very short strength in the filaments, so it doesn't have that structural similarities. So this is something we need to still look into. This is something we need to still investigate and experiment. So to conclude, so far we successfully constructed some sort of a process flow for constructing 3D models on Idaki. And we developed a prototype 3D printer for this process. And we created a 3D model with a fairly accurate representation. We have a scaled model with Naki printed using FDM 3D printer. And as I said before, the 3D printing process in terms of new materials and in terms of size, there's something we still need to look into. And yeah, I think we are way over the time limit. And that should be the end of the presentation. Thank you very much.
Thanks very much, Kim and Aaron. Yeah, we are a bit over time, and I just want to make sure that we have plenty of time for Daniel at the end there as well. We were trying to fit a lot in today's session. I will just remind attendees that they can ask a question in the chat window now if they like, and we'll hopefully have a few minutes for questions at the end. So just finally, we have Daniel Bornstein, who is a student of the Grimwade Centre of Master of Cultural Materials Conservation, who has a broad specialisation and a professional background in photographs, books, paper, objects and machines. He's worked in the private sector and with institutions including the Powerhouse Museum, University of Melbourne and National Library of Australia. Today, he's going to share some findings of some research in 3D scanning traditional Indonesian instruments. And so if I can just ask Kim, turn your camera off and we'll hand over to Daniel.
I'll be chatting a little bit about 3D imaging techniques. So this dovetails nicely with what Aaron and Kim were just talking about there. This, just so you know, is based on my minor thesis project, which was fed by this the same research, but it was specifically looking at imaging techniques for the instruments, and specifically I was looking at accessible imaging techniques for small institutions or individuals wanting to try this. So just a sec. So I was looking specifically at two instruments from the Music Archive of Monash University. So it's an interesting case study, just because the Music Archive, it's a significant collection of Indonesian ethnographic musical instruments dating back to the 19th century. For some areas, it is probably one of the most complete records of a lot of this stuff. Just because in areas, a lot of it has been destroyed by natural disaster and other things. So in some cases, this archive provides one of the most sort of complete archives of the cultural instruments that it holds. And so it's a very significant archive. Just the only problem with the archive is that it's 6,000 or roughly 6,000 kilometers from its source community. So in this case, the instruments that I was looking at were both from the Sumatra region. So they're held in the collection store in Clayton, which is a very, very long way away. So you can imagine that in order to increase access, they're looking at digital or virtual access. And so the way that they're doing that at the moment is through the Figshare platform. And the Figshare platform is quite a good platform, so it allows them to host things like audio recordings and things like this, but it only hosts 2D visual assets. So they can put photographs in, but not 3D assets. In my research, of course, I was asking, can 2D assets make effective digital surrogates for objects which are defined by their three-dimensionality? So that's what Aaron was just saying a moment ago. You can record the sense of the shape of an object from a photograph, but how much of it can you actually, or how much of what makes the object culturally meaningful can you actually capture it in that photograph? So in the case of musical instruments, of course, they're defined by their three-dimensionality, so they're acoustically defined by it. The internal shapes and resonating chambers within them are very important for the sounds that they make, which of course, and also for the use and the way that they're played, which contributes to the way that they're used as cultural objects. So I've posed this as a question. Obviously, my answer, or the answer that I think, is no. So for the reasons that others have just discussed, I think that 3D assets are a really important thing for many cultural institutions to look into. As my background is in conservation, conservators generally like to keep things, I can't remember Aaron's exact phrasing, it was something to the effect of static and dead on the wall or something like that. And that tends to be how we like our objects. But in the case of musical instruments, I think that really doesn't sort of capture what's important about the instruments. And as conservators, I think we're generally looking to manage cultural transmission, or the transmission of cultural meaning through an object's change of state or condition. And so if that's the sort of stated aim, then you really need to be thinking about making sure that you're transmitting all the aspects which make it culturally meaningful. And so I think 3D is a really good way to do that, or to look at it. So there are lots of 3D imaging technologies available. I'm not going to talk about all of these, although I think Kim and Aaron did just sort of mention quite a lot of these, and it looks as if they're looking into a lot of them. But in my research, I looked at 2 of them in particular. So photogrammetry, because this is by far the most accessible and where most people looking to get into 3D will start out, and also X-ray micro CT, because it is the most comprehensive. So as Kim said, you can get extraordinary detail out of it. But it does have drawbacks and limitations. Well, both of them do. I think we've already sort of discussed what photogrammetry is, but basically it works. It's sort of the same principle that the way your eyes can calculate depth perception using sort of the distance between them. Photogrammetry kind of does that, but on a scale where you give it lots and lots and lots of different points rather than just 2 eyes. You give it usually between about 150 to 250 of them. So you just photograph the object from lots and lots of different perspectives. What this means, though, is that since it is generating the 3D data from photographs, you can do it with virtually any camera. So it's a very good starting point, because most institutions will have some kind of setup for 2-dimensional digitization, and photogrammetry can use that setup. So you don't actually need to buy any new equipment. For my own research, I was looking at the Grimwade Centre. So my background is in photography, so I found photogrammetry very easy, but I know that lots of other people don't have a background in photography, and lots of objects are quite difficult to light. So I came up with a workflow, or well, I didn't come up with it, I adapted a workflow which uses cross-polarization and turntable capture in order to make it as easy as possible to get repeatable results, and it's also a scalable process. So with minimal purchase of new equipment. So this was about $500 to $1,000 worth of new equipment that the Grimwade had to purchase, and you can see in the bottom left there, that's basically all of the that's everything it needs. So it's a camera, the turntable, the strobe, which is on the camera, and just a computer for processing. So I won't talk too much about the process. As far as the assets are concerned that you actually get out of that, so as was indicated by earlier speakers, you really only get sort of the exterior details, although in the case of the slit drum there, you can see that it actually did get decent results from the inside of the of that slit drum there, and you could probably actually clean that up in post. But obviously of the sealed instrument there, the Gendang, there's absolutely no way that you could get any data from inside that drum there. So in terms of reproducing it, or taking like an acoustically accurate document of that, there'd be no way that you could do that using photogrammetry. But still, that you can see that these would be useful assets for lots of different things, and combined with a sound recording, these could be quite a good digital resource. So I looked also at X-ray micro CT as well in the study, and so this works very similar to the way that X-ray medical CT does. So you can see on the left there, it's basically a stack of a whole lot of X-rays, so the same that you would get if you broke your arm or something like that, and it just takes about 1,800 of them were used for this model, and it just stacks them all together and is able to sort of get a model from that. And you can see from the middle on the right there, that's the what's called a DICOM stack. So it's like the same as you would get with if you've ever had medical imaging done, you'll often get this. You can see extraordinary detail in there. It's also geometrically accurate for the inside and the outside. And in this case, I was able to image the inside there and determine, well, in this case, the skin was stretched on around what's called a flesh hoop, so like the ring that kind of tensions it. And I wasn't sure what that flesh hoop was made of, but you can see from this data, and it's probably moving too fast to actually see it there, but or you can on the right, the flesh hoop is made from little strips of bamboo which have been twisted around, and then the skin has been kind of rolled around it and then tension applied to that. And so that's something that describes the construction of the artifact, which is something that as a conservator, we're always looking to sort of document. So if somebody wanted to recreate this, they could do that from that data, and we didn't need to saw it in half with a bandsaw, which is always a plus when you're dealing with cultural objects. As was indicated earlier, it's a specialized process, so I couldn't do this myself. This is the machine. The machine, I think, costs between $250,000 and $500,000, so it's a good device. This one was quite a bit quicker than the one that Kim used, I think. So it only took about 2 hours for the sort of complete imaging, and then another sort of 3 to 4 hours for the post-processing. And it really only took that long because I was very picky about what I wanted. And also Dr. Jay Black, who you can see there on the left, who is very good at what he does, just hadn't really imaged ethnographic musical instruments before, so it's a very specialized thing. But together we were able to sort of come up with this mounting system that you can kind of see in the bottom right there. So basically it's put inside a PVC tube which protects it from the machine, so there's no way that there can be a collision or anything like that. And there are foam blocks put inside there, and the foam doesn't come up in the scans, which is why I've had to render them in the colors there, because it's a different density to the wood there. So you can get very clean, good data from this method. It's very safe. There's actually there's a standard or a document that's come out with there's a project called the Musicius project, which actually describes or details a process for CT scanning of musical instruments. And there are open architecture systems, so you can scan very large objects with this method, but it is quite specialized. As I said, it's not necessarily that accessible, but with that said, because it is used so much in industry, there are commercial operators. So it's kind of, if there's a particular research project that you're looking at or a particular object that you really want to see, you can sort of pay to have it done, and that brings the cost down to sort of maybe between $500 to like a couple of $1,000s per scan, which does, I would say, put it in reach for specific research projects. So just to give you a sense of what you can get from the data, you can see on the right there, that's the mesh that's generated. It's a beautiful, beautiful mesh. So there's about 5 million faces in that mesh. It's lovely. And you can do all sorts of fancy things with it. So on the left there, there's a false color density map of the instrument. So basically you can see areas of density. So the more dense areas are the yellow areas and the less dense areas are the red. So you can probably guess from that this can be used for acoustic modeling. Some manufacturers claim like sub-micron levels of accuracy and resolution for these scans. So they're really amazing data. You can use them for all sorts of things. You could, or people do use them to work out, say, what sound an instrument can make without having to smash it with a drumstick or even an air drumstick. Just to sort of compare them there, so obviously this is external data only, but this is the photogrammetry scan overlaid onto the CT mesh as well. So the photogrammetry scan is in blue there, and the CT mesh is in red. So just because the meshes are different, so particularly the strap, I wasn't able to actually get like a quantitative measurement data, but you can sort of just eyeball it here and see this drum's only about 10 centimeters long by 7 centimeters wide, so it's about kind of this big, very small. So you can see they're surprisingly accurate. So even though there's a couple of orders of magnitude difference in the resolution there, so about 1,000 times difference in resolution, the overlay is pretty close. So you can see a big blob of red on kind of the side of it. Sorry, it's moving very fast. I can't actually control it. It's a GIF, but there's a big blob of red on kind of the bottom, and that's where the foam block was in contact with the drum. So that's kind of pushed it in a little bit, and so there's a difference there that's in the CT mount, and obviously the straps are positioned differently in the two scans, but by and large, it's sort of surprisingly accurate data. So you can actually overlay the textures generated from photogrammetry. So like the surface appearance that's generated photographically, you can overlay that onto CT scans if you can get them close enough. That's not something that I've done here, but it is something that I know is done. So unfortunately, I've only got 8 minutes to talk about it, but generally, as many people know, if you approach somebody and ask them to talk about their thesis, they'll talk for hours, so I could happily, but I'll cut it off there. So basically just something to think about is that those are two methods which are very accessible, show very, or capture very different data, and are two things that are definitely worth considering for anybody looking into digitization of musical instruments or any three-dimensional objects, and something that I think a lot more institutions should be thinking about, and I'm sure we'll start to think about there. I've just got a few acknowledgements here. There are a lot more acknowledgements due as well, I think, but those are kind of the main ones that contributed and helped me with my thesis. I've also got a little QR code there that says scan the code to see the 3D assets. Now, I don't actually have the permissions yet to host them, so they're not up at that link, but by the time you see the recording, hopefully they will be. And I have put in, just as a little placeholder, there's a little scan of a little bronze tortoise, so just if you feel like you really want to scan something and look at the 3D thing, you still can there. So as well, you're welcome to email me, so my email address is at the bottom there, so feel free to take a little screenshot of this slide or anything like that, and otherwise I will wrap up there. Thank you very much.
That's great. Thank you very much, Daniel. Sorry, we are running quite a lot over time, but we've just got a couple of minutes left. If I invite the speakers to turn their cameras back on. We did have one last question come in from Amy, who asked about the opportunity to perhaps use 3D printed UDIKEys in exhibition environments to give people access to perhaps play the instruments. And I think Aaron answered it, but it might have only just gone to the panelists. So Aaron, did you just want to give an answer to that question? And perhaps even you've put a comment in there about another application of bringing these projects together with the air sticks and the sound of the drums and that kind of thing.
Yeah. So the answer to the question of had we thought about it, yes, we have thought about it. We've thought about bringing scanned instruments into gallery spaces so that people can actually play the instruments. I mean, that'd be great. It'd be great as a way of providing that kind of experiential learning and access while saving the originals from wear and tear, which is, something that is a great concern for people working on the conservation and curation side of things. I also thought, as Daniel was working there, another great application that could come out for that kind of gallery floor use as well. Why not program some air sticks to actually play the voice bank of sounds from drums like the ones that Daniel had scanned. So that's another sort of crossover that could potentially come out of this. I mean, the air sticks could really be used for like literally anything. So I mean, they're an extraordinary resource in their own right. But look, all the resources that come out of this are pretty special. So it's really great privilege to be able to work with everybody on this.
Alon, did you have any comments on using the air sticks for different sounds like that?
You can't blow into them, but that would be the next. That would be the next stage. But yeah, they're a gestural instrument, so they're really great for shakers or for triggering samples through gesture. And yeah, the closest we've done to that is in the Granger Museum. We took samples from the Granger instruments. For those who have heard of Percy Granger and his whips and chains and instruments, and that was great because we got to play his instruments alongside the samples and play around the instruments and trigger like the kind of ghost sounds of the instruments around them. So yeah, it's definitely something that I like doing, is taking samples from instruments.
Look, I think we'll wind that up there because we've come to the end of our time today. Thank you so much for all these presentations. I think I really feel that there was a great thread running through all these presentations, which is thinking about how we capture, say, the experience of playing, the sounds, the activity of playing, because these objects are more than just a standalone object in itself. It's been really interesting, and I thank all of our speakers today for their presentations. I'd also like to thank Matt for capably handling things behind the scenes there as well. And just before we sign off, I just want to point out we have our next instalment in our DH Lab webinar series coming up really soon on Tuesday the 6th of September. That'll bring together a couple of specialists in history and education who are going to share their experiences designing games and VR experiences and how we learn and engage in immersive and interactive spaces. So as attendees for this one, I'll send you an email with details for the next one, and I'll also send the video out to everyone who's registered today. With that, we'll sign off. Everybody have a fantastic day. Thank you.